Welcome again, everyone. My name is Alexandre Chabot-Leclerc. I'm the lead instructor here at Enthought, and I'll be guiding you through this webinar. What I have here is our agenda for today. So I'll go through a first intro about who is Enthought and what do we do, and then we'll get into the meat of the webinar. We'll talk about Python, what it is and how to get started. And then I'll guide through an overview of the syntax differences between MATLAB and Python. And then I'll discuss a little bit about Python and how it compares to MATLAB in the context of different examples, data analysis, some machine learning, and how to build graphical user interfaces. At the end of the webinar, there will be a formal Q&A where we'll pick the most popular questions and I'll answer them out loud. If you have any questions as we go, you can type them in the questions box. My colleague will do their best to answer as we go. And at the end, all registered attendees will receive a link to this recording. So if something comes up during the recording and you want to catch up later, you'll have access to that. So the goals for today's webinar is to help you decide whether migrating to Python is the right choice for you and your organization. And if you do decide to do so, we want to help you get started as fast as possible. So this is not a course. There'll be interesting content, but this is not like a course on Python. So this is not, we cannot cover all the details in the webinar format. So we also wrote a white paper that some of you might have downloaded already. I'll talk about it some more at the end of the webinar. You can download it at the link below, and my colleague will also paste it in the chat box. So it's a more extensive coverage of the things I'll cover today. So a little context, decide if this is for you. So this webinar and Python is definitely for you if you want to know more about the conceptual and technical differences between MATLAB and Python. It's also for you if you're currently using MATLAB and you're frustrated by some aspects of it, like packaging, naming, the difficulty of using some good software development practices like unit testing, and if you want to know how to get started with Python. Unfortunately, it's not the best choice for you if you rely heavily on some features of MATLAB, like Simulink, or its FPGA support, or its code generation for embedded systems. Unfortunately, those are things that don't have good equivalent in Python, and in some cases, even in open source alternatives. So who's Enthought and what do we do? So we are a company that does scientific and analytic computing. Sometimes it's not so clear for people what that means, so I picked an example to explain that. So it's a project called the Microreology Lab that we did in partnership with Procter & Gamble. Rheology is a term that means the study of the flow of matter. So as you may know, Procter & Gamble develops things like shampoo, for example, and the fluids they design are fluids that have never existed before, and they have to figure out their properties to know how, let's say, how hard you have to press on the shampoo bottle. So historically, they would have to produce pretty large volumes of those fluids and then put them under large pressure to measure their properties, which was very expensive. So there's a team of Harvard scientists that figure out that if you put tiny particles of those fluids inside of another liquid and then optically with the microscope looked at their Brownian motion, you could infer and measured some characteristics, you could infer the properties of the final fluid. So we partnered up with the Procter & Gamble team to build a custom application with custom visualizations that would visually track the particles in real time and calculate all the properties they needed. So that's a common example of what we do. We write software in order to help scientists or engineers speed up their workflow, allows them to make decisions faster, have a higher level view of what they're doing. And everything you're seeing here in the application, all of it is interactive. You can access it also drop down at the command prompt and use all the power of Python to do on-the-spot analysis of what's happening. And we've been doing that for over 15 years. In the recent past, we've been focusing mainly on artificial intelligence for oil and gas, manufacturing, aerospace, and biotech. In addition to consulting, we also develop software, which I'll talk about in a second. We do training and provide support. It's worth mentioning support. So it's often something mentioned about Python that it doesn't have, because it's an open source language, it doesn't have sort of a centralized support. So we offer personalized email, phone, real-time support, the same way that, say, Red Hat offers supports for Linux, so Linux is open source, but you can talk to Red Hat to have corporate support. Our softwares have been downloaded by more than 1 million users, and we're headquartered in Austin, Texas, with additional offices in Cambridge, UK, and Mumbai, India. A quick word about the softwares we create. One of them is our Enthought Python distribution, which is a version of Python, or the Python that we compile ourselves. We run all the tests. It's also a collection of the core packages for scientific computing, which we also run the tests for. We create dependencies, analyze the dependencies, make sure everything works. So it's rock stable, and we've been doing that for years. We also produce the Canopy integrated development environment, which I will talk about in a moment. And we also have our deployment server, which allows companies to have behind their firewall their own custom packages, and also mirror other packages if they want to, so they can control access of distribution of their packages within their organization. We also have plugins for Excel and LabVIEW that allows you to talk to Python from those applications, and some more specialized products in the oil and gas industry. For training, we have a handful of classes that we teach in the United States, in Canada, and Europe. We do them both in what we call open form, so any individual can just attend those classes, and also corporate on-site classes where we go to your company and teach your team, your group. And on the right-hand side is a handful of topics that we cover through consulting, so some energy, manufacturing, aerospace, semiconductors, consumer product, and finance. So our consultants all have PhDs in related STEM fields, so they're not just computer scientists or just programmers. They have deep expertise in these various domains, so they can totally talk with our customers one-to-one, and talk to the engineers and the scientists there. So let's get started with Python. We're going to cover the what, the why, and the how. So what is Python? It's a general purpose programming language. That might scare you if you come from MATLAB, who's really focused on scientific computing. I would argue that being a general purpose programming is actually a great thing. Means that it's actually a more flexible tool that was designed for programming first, but it has a really large active scientific and engineering community, and also data science that has developed great packages for doing data analytics, visualization, array computing, computational science, etc. Python is free. That always puts light in the eyes of people. So free both in money and as in freedom. I'll talk about that some more in a moment. It's from the technical point of view, it is interpreted and interactive. That's very similar to MATLAB. That means you have a command prompt where you can type some code and get an answer immediately. You don't have to compile your code, wait for compilation to complete. Python is object-oriented. That doesn't need to scare you if you've never done any object-oriented programming. It means that everything in Python is an object that stores data and has behaviors that go with it. But Python is super flexible, allows you to program in a more procedural manner with just functions and statements if you want. You can also do more functional programming, so it's a very flexible language. But it also makes it really easy if you do want to define your own types to just do that. The code is also portable. It will work across platform, Windows, Mac, Linux without problem. And it uses dynamic and strong typing. So that means you don't need to specify the type of each of the variables you work with. So again, very similar to MATLAB. And uses strong typing. That means that it won't under the cover do type conversion for you. So for example, it won't convert a number to a string if you add them together. Now, why would you want to convert to Python? So one reason, cost is often mentioned. Sure, free is appealing, but nothing is always completely free. So I think even though it's a good reason, I don't think it's the best reason for converting to Python. I would think that the freedom of free is actually a better reason. So there's no lock-in. You can change implementation, change a different Python implementation, change platform. Also, your code can still run even if you stopped paying license. So that can greatly improve the chance of survival of your code. It's also a very flexible language. So because it was designed as a general purpose language and then people created a lot of extra libraries for it, you can do everything in one language. You can do hardware acquisition, data processing, simulation. You can develop applications, even build web services, do 3D modeling. So that means that within one organization, you could have a single language for the person who does hardware, the person who does simulation, and someone who does finance. Python has a really large, super fun and great community. There are three main organizations of conferences. PyCon, which is more of a general conference. SciPy, focused mainly on the scientific ecosystem. PyData, which overlaps a little bit with SciPy, but has a focus more on data science. Just as a measure of the size of the community of Python, there are currently more than 800,000 questions on Stack Overflow. For comparison's sake, there's about 75,000 for MATLAB. Another thing that speaks of its popularity, as of yesterday, there was 117,000, more than 117,000 packages on the Python package index, which is the repository of Python packages, the main repository. That's not counting all the things that are on the various code hosting platform like GitHub or GitLab or Bitbucket. And Python is often in the top 5 most popular programming languages, like the TOB index and the PYPL index. So it means that if you're looking for Python programmers, there's a lot of them out there. And if you are a Python programmer, it means that there's a lot of job for you. So how do you get started? I highly recommend installing Enthought Canopy. I've taught Python to hundreds of scientists and engineers using all the tools you can think of, all the IDEs, and this is by far the easiest way to get started, and it's the application that gets the most out of your way as well. So it's a free license, it's a one-click install, so you just download one thing, and it comes with the interface that I'm showing here on the right, and it also comes with our proven scientific Python distribution, so you have all the core packages that you need to get started and replicate the MATLAB experience. And all of those libraries are also linked to the fastest implementations. So for example, Intel's MKL library for doing fast Fourier transforms in linear algebra. And all of the packages we distribute are tested, and we have dependency information to make sure that the environments you create are consistent. In addition to this clean layout here, it's possible to add additional panes with our graphical debugger and variable browser. So the variable browser in the upper right is equivalent to the workspace in MATLAB. It shows you all the variables that are currently defined in your environment. You don't have to be in debug mode in order to show it. You can just display it at your convenience. And as you debug, you have what you would expect from a graphical debugger. So you have buttons to step through the code if you prefer that, but you can also drop down at the interactive prompt and execute code, change values, etc. So if you want to download Canopy, there's the link below here, store.enthought.com/downloads. As you might be aware, there are two main Python versions, two main branches, Python 2 and Python 3. If you're starting from scratch on a new project, you should choose the Python 3 installer. And you should choose Python 2 only if you need to work with an existing Python 2 project. So Canopy comes with a core of packages. If you want to install more that don't come with the installer, we have a graphical package manager where you can look for what you want. And then it's a one-click install. Canopy will make sure that the environment you create is safe and consistent. So it'll ask you to confirm that you do want to install the package. But of course, you're not limited to the packages we're providing here. You also have access to the 100,000 and more sort of Wild West packages on the Python package index. Canopy also integrates with the the Jupyter tool, the Jupyter Notebook, which allows you to keep your code, results, figures, and text together. It was certainly an inspiration for MATLAB's live scripts that were introduced in 2016A. This notebook was released first under the name IPython in 2011, and right now it has a giant following. This summer they had their first JupyterCon conference with lots of people from O'Reilly, for example, and other really large companies. So this is a great tool if you want to communicate ideas or do exploratory work. You can show images, add links, videos, other web pages, display LaTeX equations. It's a really, really great tool. So let's talk about some code now. So in order to walk you through the differences between MATLAB and Python, I created this tiny script here that generates the figure on the right. So I'm plotting 3 sinusoids as a function of time. So I start off by creating an array of 3 frequencies, create another array of 200 linearly spaced values between 0 and 2, and then I select the first 100 elements of this. Obviously, this is not necessary. I could have created an array only of the only 100 elements before, but I want to show the differences between subsetting or slicing data between MATLAB and Python. Then I set the hold state to on so that whenever I plot, the lines overlay onto the same figure. And then I iterate through each of the frequency where I calculate my sinusoid for a given frequency, plot it as a function of time, and also label each line so that when I show the legend later, each of the lines are labeled. Then I display the legend and save the current figure as a PDF. So on the right-hand side, I'm going to replace the figure with Python code, and I'm going to walk you through the differences. So as you'll notice, the match is almost 1-to-1. Basically have the same lines of code, except for these 2 lines at the top. And those are called import statement. So I mentioned earlier that Python doesn't do computational programming out of the box. Those capabilities are provided by packages, so developed by not necessarily the core developer of Python. And in order to use them, you have to do what is called to import them to let your current script or your current session know that you want to use them. So here I'm importing NumPy under the alias NP. So NumPy is the package providing arrays or matrices that you would expect if you come from MATLAB. And the second package, matplotlib, is a library for plotting, which is very, the top level API, the interface is really similar to MATLAB. Actually, it was heavily inspired, if not copied, on the MATLAB API when it was originally created in the mid-2000s. So you might wince at the idea of importing things every time you need them. It actually has a few great advantages. The first one is that whenever you open a script, you see exactly what your script requires to run. And second, because functions can be implemented in different packages, because you usually call them with the package prefix, it means that they have their own namespace, they have their own qualifier, which means that you don't need to come up with weird, unique language names for different functions. You can give them descriptive names and not fear that they will clash with other packages, because people will usually call them with the package prefix like this here. Another thing you might notice, there are no semicolons in Python. So Python doesn't display any output unless you ask it to, usually with the print function. So let's go through the code. First, I define a list of 3 frequencies. So this list is a Python data structure, not NumPy. It's similar to a cell array, so it's an ordered sequence of objects. They can be of mixed types. Then I create my array of linearly spaced values. Notice the function name is exactly the same. The only difference is the NP prefix to say that this function comes from NumPy. Notice that I've named the variable slightly differently. So on the Python side, I'm following the Python style guide. So it's a document, part of the Python language actually, that doesn't enforce but suggests a really good style guide to increase readability and therefore maintainability of code. Then on the next line, I slice the data. So I pick the first 100 elements. So two things to notice here. Python uses zero-based indexing, and the upper bound is not included. So again, that you might think that this is a bit strange. It has really great properties that makes things actually really nice and less likely to make off by one errors. I won't talk about them now, but there's a whole section of the white paper dedicated to it. And the second thing you might have noticed is the use of square brackets instead of parentheses. So in Python, every time you access an element in a data structure, this is done with square brackets or for lists above. And the parentheses are reserved for calling functions or for grouping elements in, say, an equation. Then I don't need to set the hold state. Hold is, quote, on by default in Matplotlib. Then I iterate through my frequencies, create the sinusoid. Again here, the sine function and pi are both provided by NumPy. And then I plot the sinusoid versus the time. And I also label my function, label each line with the frequency. Notice here there's an equal sign within a function call. So this is Python's syntax for specifying optional, what is called keyword arguments. So it makes it really, really clear which one is the argument, which one is the value. And this is used here on the calling side of the function, but it also can be used when you define a function to define default values, which is really, really, really easy, really clean, much easier than defining keyword values in MATLAB. Then no end keyword in Python. The white space is what defines what is part of the for loop or what is part of the function. This is great for readability. It's something we do anyway, so it's actually encoded as part of the language. Then I show the legend. I don't need to pass any arguments. Matplotlib is going to use the labels that are part of the plot to show the legend. And then I save the figure to a PDF. Again, Matplotlib knows that I'm actually talking about the currently active figure. There are ways of working with, for example, figure handles and axes handles, but I'm sticking to sort of the higher level closest to MATLAB API here. So as you see, the code is almost exactly the one from one side to the other. So if we look at the output figure, that's what Matplotlib created. It has the figure was created exactly as it was on screen. No weird mismatch between what's on screen and what saves to a file. Everything is anti-aliased and has been anti-aliased since 2002. It has built-in LaTeX rendering, both for LaTeX rendering on screen inside of the figures, but also exporting to a format that can be included in a LaTeX document. So, quick summary of this. Very similar syntax in both languages. All of the things you've learned with MATLAB, many of them will have a one-to-one equivalent in Python. So it's really easy to get started. NumPy is the package you want to work with if you want to do numerical computing, work with multi-dimensional arrays. And Matplotlib is the main package for doing visualizations, but there are also many other ones that offer either web-based visualizations or higher level, let's say, statistical visualizations. The second example I picked is doing analysis with a package called Pendous, which provides a data structure called a data frame, which would be an equivalent to tables in MATLAB. Pendous started in late 2000s. The first book about it was published in 2012 by a Pendous author, Wes McKinney. Tables were introduced in MATLAB in 2013. So in order to show how that would work in Python and to show some of the aspects of working with objects in Python, I'm going to actually walk you a small data analysis project of analyzing tip data. So again, I'm importing Pendous as PD. So I'm going to use the PD prefix to use Pendous functions. Then I read CSV data using the read CSV function. It's a really, really fast CSV reader. The last benchmark I saw actually beats MATLAB's CSV reader. Pendous also has a lot of really powerful functions for reading data from databases or even parsing tables from web pages. So no need to write your own web parser. And what it creates is our data object here, or data frame, which is a labeled data structure. It's a tabular data structure with column names and also row labels that are just numbers in this case. And this allows us to store mixed types together. So I have a few floating point columns, a few string columns, and also some integer columns. And right here at the top, I'm calling the head method. So that's kind of like a function, but attached to an object. And because it's attached to the object, it knows where to look for data. I don't have to pass any arguments to it. So head here shows me the first 5 rows of my data frame. There's a handful of other super useful method like info here that tells me the type of each of my columns. Some of them are categorical, which is a great feature. Allows for saving quite a bit of memory if you have large data sets. Also tells me the memory usage of my data frame. And describe gives me more of a higher level overview of the data contained in the data frame and less about the data structure. So some of the statistical moments, the count is the number of non-missing values. So I have about 244 lines in this case. Pendous follows the regular API in Python of using square brackets for accessing data. Here I'm creating a new column called percentage, which is the percentage of tip relative to the total bill. So I have the tip column here divided by the total bill column multiplied by 100. So again, I'm using the square brackets to access data, and I can access data by name because my columns are named. The backslash you see on the right is the symbol Python uses for line continuation instead of the dot or ellipsis in MATLAB. Notice here there's no for loop to iterate through all of the elements in the array. It uses vectorized operations just like in MATLAB. Using methods also works on data you pre-selected, so you can chain statements. You don't have to assign it to variables every time. So here the maximum tipper tipped 71%, which is quite a generous tip. And if we wanted to look at what row that corresponds to, that's also very easy with the argmax method that tells us which row had that value. If you want to do computations on the whole data frame, you don't have to pick only one column at the time. So here I'm looking at the median data, and Pendous gives us the median data of all the numerical columns. So the code here doesn't change even if we have 10,000 times more data. Another thing I want to show here is the flow of information when working with Pendous, also very common when working with Python in general. So we start with data on the left. Actually, let me say, so what I'm trying to do here is to calculate how much money did this, let's say, restaurant made on a given day. So I have data for 4 days. So I would like to group by day, which I do with the group by method. Then I'm only interested in the total bill column. I'm not interested in the tip column. I'm not interested in the size column. And then I can say I want the sum of those results. So you can see the data goes from left to right. It's really readable. I'm not nesting function calls. And this chain I'm building, I can stop it at any time and assign it to a variable for, let's say, debugging or caching, or if the line gets too long and it affects readability. And it's really easy to add more things to my pipeline. So let's say if I want to turn that into a plot, I can do .plot.bar. So now I have a visualization of my data. So this way you can interactively, if you're working interactively, you can build a pipeline of your transformations, and really, it's really easy to go from left to right. Like, okay, I have data, it goes through this group by filter, I extract a column, I do a summation, and then I plot the data. And these data structures, the data frames, they behave just like arrays. You can pass them to all of the NumPy functions. There's no need of converting the data frames between tables and arrays, unlike MATLAB where you often have to convert between arrays and cell arrays and regular arrays and tables. My third example is to do some machine learning with a package called Scikitlearn, again to show some examples of common use cases or common pattern when programming in Python. Scikitlearn, you might have heard of it if you're looking into Python, is one of the most famous packages. It's used by lots of organizations like Netflix, YouTube, Google to do machine learning. So the example I'm going to do here is some handwritten digit recognition. It's a common example. So the little code snippet I have here loads some data. I have just short of 2,000 samples. Each of those samples, each of those numbers, each of those handwritten digits is made of 64 pixels. So I have one here in the upper right. To be honest, I'm not sure what that is, but we'll see in a second what Scikit-learn thinks it is. Then, because I'm a good boy, I separate my data into a training set and a testing set. And I keep about a third of the data, so the test size about 33%. 33%. And you can see here this mix of positional arguments, so digits the data and digits the target, and keyword argument, so the test size and random state. So it's really readable, and you know what values you're defining. So the next step is to define my model, my estimator. So in this case, I'm going to use a support vector classifier. It comes from the SVM module of Scikit-learn. Again, it has some parameter that I'm passing to it that affects the classification. So this estimator model is what's going to do, this is what we're going to train and what we're going to use for prediction. So I go ahead and I fit my model. I just pass the train and test data, the training data and the training labels. I don't need to pass any other arguments. All of those arguments, all the settings for that estimator have been passed during creation. And then I can predict. So I predict some new data that the model has never seen, and I use this slicing pattern at the end to show the last 5 elements, and I compare that with the last 5 targets. So the model here correctly predicted the new data, and the image you see in the upper right is actually the first 8 here. So I'm not sure I would have said an 8, but Scikit-learn correctly predicted that it was an 8. And we can look at the prediction. Again, the model keeps track of the best parameters. So if you pass in if you pass the test data to the score method, it will be able to give you the accuracy of the model. So here it's close to 99%. So the nice thing about this and this interface and this API and the fact that we're using objects for the classifiers, Python objects, is that if we decide to say try a different model because we're not satisfied with 99% accuracy, I can say replace this with a random forest classifier with its own arguments. So here the number of trees in the forest, and all of the rest of the code stays the same. In this case, you'll see the accuracy dropped a little bit to about 97%. But the fact that Python is object-oriented makes for really readable and easy to maintain code, because you can encapsulate data and behaviors. And my last series of examples is doing application development and show how you can go from prototype to product using the same tools. So some of the libraries I'll talk about here are called Traits UI, Chaco, and Mayavi. So the first one I have is a tool to visualize principal components in faces. So I have a set of photos. They're all 64 by 64 pixels. And we extract the principal components of those faces using Scikit-learn. And the entire code you see on the left is used to generate the user interface on the right. That allows me to explore the effect of the 8 first component on the look of the face. So this is made with the package called Traits UI and Chaco for the visualization. So it makes it really easy to explore your data and visualize your data. Second example, a little bit more advanced. That's about 275 lines of code total. So what I have here is a forest fire simulator. The code you see on screen is the entirety of the code that models the forest fires. But the other code is what creates the UI that allows you to run through steps of time and visualize at a higher level of abstraction the effect of the various parameters. So in this case, the rate at which trees grow and the rate at which fires happened. So really easy to start with the domain-specific model and then create a visualization, a special view, a custom visualization just for your domain-specific models. My third example is another application made with Chaco. This is about 175 lines of code, of which there's about 25 lines of imports. So this is a real-time audio analyzer that samples the audio card. The graphics update about 60 frames per second. Right now it's capturing audio from my sound card, but you can imagine that you could connect this to some hardware and easily build custom visualization for your experimental setups. And the last example is something built with Mayavi, which is a tool to do 3D visualizations. Again, a slightly larger project at 250 lines. So super smooth graphics, uses OpenGL for all the rendering. So the important thing here is those three packages I just mentioned. So Traits UI, Chaco, and Mayavi are things we use every day in our consulting projects. They're what we use for prototyping ideas, but also for building applications for customers. So they're definitely production grade tools that are really easy to get started and be productive with. And they power things like Canopy, for example, is built with Traits UI. So as a summary, Python has a really clean syntax with a strong focus on readability, and yet it's very similar to MATLAB, so it's really easy to get started. It's a great language for scientific and numerical computing. It's as readable as MATLAB and as fast if it's linked to the right libraries like we provide in Canopy. But I think one of its greatest strength is that it's not just for scientific and numerical computing, that if you need to do two things in your application, not just number crunching, you can still stay in Python to do everything. And it's a language that's usable for fast prototyping and also for building production quality software products. So if you want to learn more, I encourage you to download the white paper if you haven't looked at it already. It's more than 50 pages. It goes much more in depth, covering the differences between MATLAB and Python. So not just the syntax, but also how memory layout is different, indexing, more in-depth syntax, etc. And then we guide you through a handful of different domains and point you to the right libraries and tips for doing different things for signal processing, linear algebra, optimization, image processing, natural language processing. And then it ends with strategies for gradually converting to Python and make sure that your code behaves the same way. So how to write tests to validate that your code behavior doesn't change, and also how to gradually change by converting one function at a time to Python and then calling it from MATLAB until you've converted your entire code base. If you want to dig more into a given domain, there's lots of books, hundreds of books published about Python and the scientific Python. Here's a handful of them that I recommend for doing computer vision, network analysis, bioinformatics, finance. O'Reilly often publishes many of them, but there are other sources for them. We'll put links to those books in the notes for the webinar. So this is great if you want to learn by your own. If you want to speed up your learning and get started much faster instead of banging your head against error messages and such. So we offer a 5-day course called Python for Scientists and Engineers, where in the first day we cover in depth the Python language, the data structure, best practices. Then on the second day we focus on numerical computing with NumPy and visualization with Matplotlib. On the third day we focus on Pendous for data analysis. Even if you're not a financial analyst, Pendous is super powerful and it should definitely be in your toolbox. Then during the fourth day, we talked about object-oriented programming, how to define your own types. We do a section called software craftsmanship about writing maintainable code, testing, profiling, debugging, sort of all the tools you need to write good quality code. And then we end with a section on interfacing with other languages, mainly with C and C++ libraries. So if you rely on those libraries for your applications. And then on the last day, we use the tools that I mentioned last, so Traits UI and Chaco and Mayavi, to build visualizations, either small exploratory stuff or large applications. And the prerequisites, you don't need any Python experience. You just need to know about programming, so general concepts. So if you're a MATLAB user, you're definitely ready for this class. And we've had great feedback about those classes. Our trainers, all of them are world-class. They all have PhD in relevant fields. So again, they're not your run-of-the-mill instructors. They're deep Python expert, but they're also scientists and engineers. You can ask them technical questions, and they have experience building the applications that I've demoed today. And yeah. So here's a handful of our customers. So we've trained clients in oil and gas, finance, social media, electronics, biotech, many in the national labs and consumer electronics. So that speaks of the breadth of Python as a scientific and engineering tool, as well as finance tool or even social media. So if you do want to take our classes, the next steps, if you're an individual trainee, you can sign up for open classes at enthought.com/training. Here's a calendar of classes coming up until the end of the year. In the middle is the class I just talked about, scientists and engineers, but we also have other classes focused more on data science or data analysis. If you have a group of 6 or 7 people and you don't see a location here that suits you, contact us through the form below, and we'll help you set up a class wherever you are and set up an open class. If you have a larger group or a team or multiple teams, you should get in touch with our account executives, Brian Allison and Michael Millett, either by email or through the form at enthought.com/contact or by phone, and they'll guide you to the best fit for your needs, and they will figure out dates. So thanks a lot for your time. At the end of this webinar, when we close the webinar, we'll have a short survey that will be sent through GoToWebinar. We'd really appreciate if you spent a minute to fill it out. It really helps us make sure that what we're providing is helpful to you. And with that, I will open up for Q&A. So my colleague Courtney here selected a few questions that came up often that thought that would be great to discuss live.
Yes, Alex, we've had some great questions from the team. Folks, if you do still have questions, please feel free to put them in this questions box. So Alex, a couple of common questions we've had. So first of all, one of the biggest ones is, what do you recommend in terms of best practices for transferring personal code from MATLAB to Python? What are some of the most efficient methods, and how would somebody get started?
So first thing you should do is to write tests. So you should not just document, but you could write code that verify the behavior of your original MATLAB code. You don't have to figure out what bugs it has, but you have to confirm the behavior, map basically its behavior. And then you can reuse that data to when you write your Python code to make sure that the behavior is exactly the same. So there's a section of the white paper that addresses this. And you can, at first, it's completely fine to basically write MATLAB in Python. So basically copy lines 1 to 1, it sometimes works. And then as you grow, as you get more experience, you can modify your code to be more what is called Pythonic. But you don't have to start with Pythonic code.
Great, that's a great start. And as you mentioned, the white paper will take people more through that. So another question we got several times was if you could talk a little bit about the speed of Python versus MATLAB. Obviously, that's a big concern for folks in looking at coming to Python. What are your thoughts on that?
Yes, so 2 things. Python is an interpreted language, so it's definitely not as fast as C or C++, for example. If you're doing numerical computing and you use NumPy, you'll get a similar speed up. You'll get similar speed, if not faster, than you would do with MATLAB if you do vectorized operations. So if you code program right, For numerical computing, it'll be the same. And if you use the right libraries, if they're linked to the right things, like we're providing with Canopy, if you do need to write like element by element for loops, for example, there are great tools like Python that allows you to write Python code, add a few type annotations here and there, and actually compile your Python code to C and then run your C library, and it runs at C speed. So it's really easy to stay in Python for most of your code, have a really fast velocity when you develop, so human development time, and then drop down to Python or C if you need for like little corner of your applications that need this little extra speed boost.
Okay. And could you explain some of the differences between Canopy and Anaconda and Spider? Kind of what are those three pieces? How do they fit together? And what are some of the differences, and when would you use one versus the other?
Yes. So Anaconda is mainly a Python distribution. So it's a way of installing Python versus various versions of Python and packages. And one of the packages it installs is Spider, which is a graphical user interface. So it's an IDE similar to Canopy, but they're not really integrated together. Whereas Canopy is built, is sort of the whole package in one. So it has a package manager, the Enthought EDM Enthought deployment manager. Sorry, I'm slipped here. So EDM and Anaconda are really similar things, ways of installing packages, creating consistent environments. But what we add in Canopy is the integration of all of this together and like one tool to get started. You don't have to figure out all the parts, all the moving parts.
And can you speak to compiling applications into executables in Python and why that's a strength of Python perhaps over MATLAB? Or if you could speak to that a little bit.
Yeah, it is possible. So to build applications that are in Python like Canopy and distribute them with an installer. Like most multi-platform installers, that's kind of tricky. But the great thing is that you don't need extra licenses for your end users. You can package Python. You can use EDM, for example, to create the Python environment, list out all the required packages, and ship that as a regular installer that a user would just double click on the icon and the application would start. So again, more freedom, another strength of the freedom of distribution.
And how does it compare to the standalone application deployment tool in MATLAB?
I am afraid this is not something I'm very familiar with.
Okay, fair enough. You have lots of answers to people's questions. You are allowed to have one you can't answer. Yeah. All right, maybe next time we'll play Let's Stump Alex. Okay, I think with that, we're going to go ahead and close the session. If you did have a question that wasn't answered, we will try to get back to you via email as well. Thank you so much for coming today. And as we close here, we're going to have a quick 5-question survey. We'd really appreciate your feedback to where we can continue doing more webinars to best suit your needs. Thanks all for attending today. Bye now.